Hello and welcome to my very last lesson on differentiation. In this lesson, I want us to look at the remaining objective, which was application of maxima, application on maxima and minima. And therefore, let's begin. I need to say that in this particular lesson, I'm just going to tackle questions, which brings the idea of maximization or minimization. The prerequisite concept that students should have at this point is something to do with differentiation, of course, and looking for minimum and maximum points, and basically that. And therefore, let's begin. We are given a question there where a man has 75 pi squared centimeter, 75 pi centimeter squared sheet of metal and wishes to make an open cylindrical container with it. Find the dimension of the container for which the volume will be maximum. So we need to have a picture of what we are doing here. First of all, the man has this amount of area, and now we think about the area of the container that he's going to make, and therefore the area he'll make is something like this. There'll be a circle, there'll be the curved surface, combine of that, and we get the total area that he's going to be making, but he only has 75 pi. The area of the circle at the bottom will be pi r squared, and the curved circle will be 2 pi r h. Therefore, we're going to say this, that the area of this one plus the area of the other one, which is pi r squared plus 2 pi r h, should be equal to the area that he had at the beginning. Okay? Let's simplify that. We get r squared plus 2 pi r h is equal to 75. I just divided all through by pi. And now we get an expression for h. You can have these 2 r h remaining on one side and this goes to the other side there. So we have h is 75 minus r squared all over 2r. Therefore, now we go to the aspect of maximization. This will be the height. Why are we doing this? So that we look for volume of the container. What will be the volume of the container? Volume for our cylinder is pi r squared h. We have everything. Now we can put the values in the formula, and therefore we're going to have pi r squared times this is h. H was 75 minus r all over 2r. Sorry, 75 minus r squared all over 2r, and therefore we just continue and simplify. You get this kind of a thing, and then at that point, while we introduce maximization. To maximize volume, it means the first derivative of volume with respect to radius is 0. To maximize volume, it means the first derivative of volume with respect to radius will be 0. And therefore, we have dv dr is equals to 75 pi all over 2 minus that one there is equals to 0. And now our business, therefore, here is just to solve this, and we'll be able to get a value of r and subsequently get the value of h. And therefore, we do this. Take this to the side, so that you have 75 pi all over 2 is equals to 3 pi r squared all over that. And then we have 25 is equals to that, and simplify that, you get the value of r is equals to 5. Remember, there's another value of r. Most likely, that other value will give us the minimum value. So for maximum value, we're going to use the 5. Okay? And therefore, if that is our r, then h will be also, you put the value of 5 in the formula for h, and you solve that, you get h is 5 centimeters. Shall I say this? That also, if we take the radius to be a negative figure, because the square root of 25 is also negative 5 or 5, if you take the negative 5, it will not look sensible. So this makes a lot of sense to get r is equals to 5, and subsequently h is equals to 5. Let's go to another question. We're told that a square sheet of metal has an area of 100 meters squared. An open rectangular tank is to be made by cutting equal squares from the corners and bending the sides up. So find the height of the tank for which the volume will be maximum. This is the sheet that you have whose dimensions are 10 by 10. That 10 times 10 will be 100. Okay. Now let the dimensions of the squares that we are cutting be x. So let the squares be x meters. The squares will be x by x, and therefore the dimensions of the tank will be 10 minus 2x. And I need to show you where that's the case. The length here is 10, but we have cut an x, we also cut another x here. So we have subtracted 2 x's. So you have 10 minus 2x to get that dimension. It's the same here because it is 10 minus an x there and another x. So that you get 10 minus 2x. So those are the base dimensions of the tank, but height will be x, because when we bend up, these ones become the height, and also this one, and all that, and you shall see that in the next drawing. Yeah, here it is. So we have cut and bent upwards, so that these ones become the height, these ones become the height, those ones there, that one is the height, that is the height. So you close them and then it will form a height. The length and the width will be the same. It is 10 minus 2x, and the height is x. And therefore now volume will be 10 minus 2x times itself, and we multiply that by x. And so volume will be, if you simplify that, you get 100x minus 4x squared plus 40x squared minus 4x cubed. So to maximize that or even minimize it, it's a cubic equation. We need to find the first derivative and equate it to 0. Okay? Remember, the values of x that we're going to get here are two answers. One should lead us to getting a maximum volume, the other one to be a minimum value. But differentiating that, you get 100 minus 80x plus 12x squared. Solve that one using the knowledge you have about quadratic equations. And you get the value of x is 5 or 1.67. When x is 0.5, sorry, when x is 5 meters, it is not sensible, because you see this will be 5, that's the value of x. This will be 5, and it also be, this is also 5. So 5 plus 5 will be 10. That means we don't have a length for the thing that you're going to make, even a width. So we don't adopt the x equals to this, we take the other one. X equals to 1.67. And we're finished. Find the height of the tank for which the volume will be maximum. Yeah, that's the question. And that's it. Let's go to the last. In this last slide, we have two questions. And so we're told Onyango wants to fence a rectangular plot. This plot, using 100 meters square of wire. One end of the plot is already erected with a wall. Calculate the maximum area he can fence. And before we even begin, we need to have an idea of what sort of thing we're having. We have a plot like this, a rectangular one. He has 100 meters, and therefore this length, this length, and this length should be fenced using the 100 meter square, the 100 meter wire. All right. So if we say let the length of this plot to be x, it means the width will be the remainder from 100. Okay. If this is x, it means that he's going to fence that x plus two other areas, two other parts, which if you add the two of them and add this x, you get 100. That's what I mean by this statement. The width will be the remainder from 100. And therefore you say this is x, this other one here must be 100 minus x, that's 100 minus this x. Then the other answer you divide by 2 to get, you have 1 for that and 1 for this other part here. So we have the shape there. Now area will be length times width, which is x times what you have there. Simplifying that, you go to 50x minus x squared all over 2. Now the first derivative, that is differentiating area with respect to x, should be 0. This is a quadratic equation which only has a single term, either a maximum or a minimum. So we differentiate further and we get 0 is equals to 50 minus x, in which case x will be a single 50. So that must be the value of x. Okay, we don't have another value, and therefore that's the length. And the width will be 25. 25, I got it by having 100 minus 50 divided by 2. It's 50 divided by 2 is 25. Therefore, the area will be 50 times 25, which is 1250 meter square. I hope that's clear. The last question. We note that for the cuboid with dimensions as shown below, all dimensions are in centimeter. Find the expression for its volume in terms of x and show that the value of x for the maximum volume is the one given there. So this is the thing we are told, all dimensions are in centimeters. Find an expression for the volume of this thing. So what will be that? Volume will be length times width times height, which is this times that, and this third one there. Simplifying, you get x cubed plus 2x squared minus 3x. Okay, so I should say show that the value of x for the maximum volume is that one there. And so let's continue. We now maximize or minimize. That is, we look for the first derivative of volume with respect to x and equate it to 0. So dv dx, which is differentiating this, which is 3x squared plus 4x minus 3, should be equal to 0. solve this one quadratically and you get the value of x is this one or that one. This answer here is not very straight, since you see we have minus 4 minus square root of 52 divided by 6. That means this answer eventually will be negative, and you cannot have a negative answer for a length, since we're looking for height. Height cannot be a negative number. Therefore, we go for the other one there. This answer is absurd. We go to the minus 4 plus square root of 52 all over 6. Again, the square root of 52 is a third, and we can simplify the third by getting it, 4 times 13 is 52. Then you simplify, you go to that way, you can take 2 outside, blah, blah, blah. Then the answer will be that one there, and that is the answer. I hope you find the lesson helpful. This is all there is in maximization and minimization. I traditionally use the KLB textbook. So if you use any other and you find any question that you find it's complex, you can always look at it. I like your comments, your subscription, and also your viewing.